In this module we continue our discussion on electric circuits. When devices are connected from end to end, the connection is called a series connection. Here we have three resistors that are connected in series with the source. The voltage source is assumed to have no internal resistance for simplicity. The current flows to all of the devices here. The circuit may look complicated, but we can simplify this by summing similar devices such as the resistors. Here we simplify the series connection of the resistors into total or equivalent resistance, which is given here. So when resistors are in series connection, we simply take the sum of the series and we write a general expression as equation 1. In a series connection, the current that passes through is the same, so that it can be written as shown here. A general expression for the current can be written as equation 2. For the voltage total or voltage equivalent, we can use the resistance equivalent and current equivalent as shown here, or expressed as the sum of individual voltages from each resistor as shown here. So, we can express it as a general expression for the voltage as shown in equation 3 and 4. Here we have a FET simulation for a series connection. We have 3 light bulbs connected in series. When devices are connected where each of the same ends are connected as shown here, the resistors here are in parallel connection with each other and the voltage source. Here we simplify the parallel connection of the resistors into total or equivalent resistance, which is given here. So when resistors are in parallel connection, we simply take the sum of the series and we write a general expression as shown in equation 5. In a parallel connection, the current total or equivalent is the sum of the individual current. A general expression for the current can be written as equation 6. For the voltage total or voltage equivalent, we can use the resistance equivalent and current equivalent as shown here. The voltage of the individual resistors in a parallel connection are the same, so we can express it. As a general expression, equation 7. Here we have a simulation of light bulbs connected in parallel. Here we have a summary of equations for series and parallel connection for resistors. Here we have a combination of a series and parallel connection, and we are asked to find the equivalent resistance of the circuit. The approach to this problem is that we simplify the circuit first. First we combine resistors 2A and 3, which are in a parallel connection, and we get its resistance is 2 ohms as shown in equation A. For current at the combined resistor 2 and 3, we use equation 6 and we get a function in equation B. For the voltage we use equation 7 and we see that it is just equal voltages as a condition for parallel circuits as shown in equation C. We further simplify the circuit into its fundamental form as shown in the image here. We now apply series equations for this phase. So for the total or equivalent resistor we have equation 1 and its total or equivalent resistance of the circuit is 6 ohms. We can further determine the parameters in the circuit starting with the equivalent current, which is done by using Ohm's law, and we get that it is 3 amperes as shown in equation D. We can also determine the value of the current at the combined resistor 2 and 3, which is just the current in series connection, so we use equation 2. And it is about 3 amperes as shown in equation A. The voltage at resistor 1 is done by using Ohm's law, and it is 12 volts as shown in equation F. We can also determine the voltage at the combined resistor 2 and 3 by using Ohm's law. We see that it is 6 volts as shown in equation G. We now determine the voltage at resistors 2 and 3 separately, and we apply a parallel connection equation, and we see that it is given in equation 7. The value would be just the same, and it is 6 volts for both resistors. For the current we use Ohm's law to determine individually the currents, and for resistor 2 it is 1 ampere and for resistor 2 it is 2 amperes as shown in equations I and J. Here we have the complete image of the circuit with the given values. As the current flows first at resistor 1, the resistor takes up 12 volts, reducing the 18 volts by 6 volts, and we see that the parallel circuit part does consume the remaining voltage difference. Sample problem. 2 identical light bulbs, each with resistance of 2 ohms, are connected to a source with EMF of 8 volts and negligible internal resistance. Find the current through each bulb and the power delivered to each bulb and to the entire network if the bulbs are connected in A series and B in parallel connection. We refer to the figures below. For letter A. First we consider the series connection. To solve for the current in each bulb and total in series connection, we examine its properties. For series connection, the current in each device would be the same. To solve for the current, we solve the total resistance, and we use equation 1. The current equivalent is then obtained using Ohm's law, and we see that the current is 2 amperes. Next we determine the power delivered to each bulb and to the entire network of the bulbs. Recall the expression for the power by using equation 8. We see that the equivalent power is 16 watts as shown in equation A. To determine the power delivered in each resistor, we use the equation 9. We see that the power on resistor 1 and 2 are the same, and they are 8 watts as shown in equation B and C. For letter B, we consider the parallel connection. Since the circuit is in a parallel connection, then the voltages are the same for each resistor, and it is 8 volts. We then use this voltage value to determine the individual currents. By applying Ohm's law, we have the currents for each resistor to be 4 amperes as shown in equation D and E. The total or equivalent current is done by using equation 6, and we see that it is the sum of the individual current, and it is 8 amperes. Next we determine the power delivered to each bulb and to the entire network of the bulbs. Recall the expression for the power by using the equation 8. It gives us a value of 64 watts. To determine the power delivered in each resistor, we use equation 9, and we have for resistor 1 and 2 to be 32 watts as shown in equation F and G. Comparing the two types of connection, it appears that the current values are higher in the parallel connection. The power is also higher in the parallel connection. This tells us that the rate loss will be higher or the battery will be drained much quicker in parallel connection. When buying electronic devices, if you wish to reduce cost, you would prefer appliances that have lower wattage. Sample problem. 4 resistors are connected as shown in the figure. For letter A, find the equivalent resistance between points A and C. For letter B, what is the current in each resistor if a potential difference of 42 volts is maintained between A and D? First, we simplify the circuit by combining resistors or devices that are in series and parallel connection already. We see that resistors 1 and 2 are in series and resistors 3 and 4 are in parallel. For letter A, first we combine resistors 1 and 2 which are in series and we use 1. And we see that the combined resistance is 12 ohms shown in equation A. We can also see the current relationship as shown in equation B. We then simplify the parallel connected resistors 3 and 4 by using equation 5. The combined resistance is 2 ohms as shown in equation C. Here we can calculate now the equivalent resistance of the circuit which we see as a series circuit, so we have 14 ohms. For letter B. To find the current of each resistor, we continue measuring the current relation to the parallel resistors 3 and 4 and we use equation 6 and get the relationship of the current shown in equation D. We further simplify the circuit to get the value of the equivalent current which we see is now in series connection with resistor 1 and 2 using equation 2. We get the relationship of the currents shown in equation E. Now we use Ohm's law to find the equivalent resistance and subsequently the currents in resistors 1 and 2. The value of the equivalent current which is equal to the currents at resistors 1 and 2 is 3 amperes shown in equation F. To solve for the currents in resistors 3 and 4, we solve first the voltage differences at points A and C and at points C and D. For voltage differences at points A and C, we apply Ohm's law and we get that it is 36 volts. We then use this value to solve for the voltage difference at points C and D and we get that it is 6 volts. Since resistors 3 and 4 are in parallel connection, then their voltages are the same. So their currents can be done using Ohm's law. We see that the current at resistor 3 is 1 ampere shown in equation H and the current at resistor 3 is 2 amperes shown in equation I. Kirchhoff rules. There are some circuits that cannot be simplified into its basic form or just having a resistor and source, which means that can be reduced into either series or parallel connection. A sample of circuit that cannot be simplified is shown here, where we have two EMF sources that are oriented in the opposite direction of flow of current as indicated by the battery's orientation. For this type of problem we apply Kirchhoff rules. Kirchhoff junction rule, KJL. When three or more conductors meet at a junction point, the sum of the currents is equal to 0, shown in equation 10. This is based on the conservation of electric charge, which means that the total charge entering must be equal to the total charge leaving a junction. Here we have a junction point where three currents meet and we calculate their relationship using KJL. In order for the sum to be 0, then the current 3 must be equal to the negative sum of the currents 1 and 2. Such that the total current in the junction will yield to 0. Note that currents must have a direction of going into the junction and out of the junction. It cannot have all currents all going into or out of a junction point. Here we have 5 conductors meeting at a junction and we apply KJL on this system and we write it into this equation. Kirchhoff loop rule, KLL. The sum of voltages in a closed loop is equal to 0 as shown in equation 11. Here we have a closed loop circuit and we apply the KLL expressed here. In KLL we apply a sign convention to help us determine the correct orientation. In some we might misjudge the direction of the current, or we simply have no idea which it should flow, and the sign convention will help us out. Here we have 4 cases. For case A, when the direction of the loop is moving from positive to the negative terminal and the EMF has a negative value. For case B, when the direction of the loop is moving from the negative to the positive terminal, the EMF is positive. For the resistors we have cases C and D. For case C, when the direction of the loop is oriented in the same direction as the current, then the voltage difference of that resistor is negative. And for case D, when the direction of the loop is going in the opposite direction as the current, then the voltage difference of that resistor is positive. Here we have 2 cases of circuit and we remove the source and resistors and focus mainly on creating loops. For case A, here we have 3 loops. The first and second loop are easily determined. The third loop is the big loop that contains loop 1 and 2. For case B, here we have 6 loops as shown in the figure. The direction of the loop is entirely up to you. The strategy that we usually use for the direction of the loop is to orient it to have less negative values of voltages. The number of loops depends on the problem. You do not need to obtain the maximum number of loops if the problem can be solved with less than maximum number of loops. In case A we see that the right end is an open circuit and we do not include this in the loop system. Sample problem. Figure shows a circuit where it is powered by 12 volts power supply with an unknown internal resistance, and it is connected to a low-powered rechargeable battery with unknown EMF and an internal resistance of 1 ohms to an inductor with resistance 3 ohms carrying a current of 2 amperes. The current through the drained battery is 1 ampere in the direction shown in the figure. Find the current of the passing through the 12 volts battery, the internal resistance of the 12 volts battery, and the EMF of the drained battery. First we look at the junctions and determine where we see that we have 2 known currents and 1 unknown current. Junctions A and C are basically the same since the current 2 will be going out from it, so we apply junction rule, KJL, at point A and we have equation A. The current through the second EMF is 3 amperes. We draw the initial loops. We draw loop 1 and loop 2. Looking at loop 1 we see that we have the unknown EMF contained in it and both the resistor and internal resistance are present, so writing an expression for loop 1 we have equation 11. And we get that the EMF at the drained battery is negative 5 volts. The negative value suggests that the EMF of the drained battery is reversed and it is being charged by the larger EMF battery of 12 volts. Now let us determine the internal resistance of the battery having an EMF of 12 volts. Using loop 2, since it contains the unknown internal resistance and the other known parameters, we write our Kirchhoff loop rule, or KLR, shown here. We see that the internal resistance of the EMF with 12 volts is 2 ohms. Note that we have retained the negative sign of the first EMF. Using loop 3, since it also contains the unknown internal resistance and the other known parameters, we write our KLR shown here and we get that the internal resistance of the second EMF is 2 ohms. Here we have a sample problem. A single loop circuit contains two resistors and two batteries as shown. For letter A, we are asked to find the current in the circuit. Letter B, what is the power delivered to each resistor? How much power is delivered by a 12 volts battery? Refer to the figure here. For letter A, we find the equivalent current in the circuit. We apply Kirchhoff's loop rule as shown in the equation here. We sum the potential in the loop and their corresponding sign using the sign convention. The negative current indicates that the flow of current is reversed as shown by the resulting value, which is 1/3 ampere. So to correct this, we reverse the assumed direction as shown in the second figure. For letter B, we find how much power is delivered when we use equation 9. For the first resistor, we see that the power is about 0.89 watts. For the second resistor, we have power equal to about 1.1 watts. For the power delivered by the 12 volts battery, we use equation 8. After substitution, the power across point D and C is 4 watts. Sample problem. Here we have a bridge circuit as shown on the figure. Find the current in each resistor and the equivalent resistance. All the currents here are initially unknown, but they are related by some function. So we first write the relationship of the currents with each other by using the Kirchhoff junction rule. We write the equations for each junction as equations A, B, C, and D. We can reduce the two currents and express them as functions of the other currents. From equation A, we see that the current 4 is just equation A. From equation B, we see that the current 5 is just equation F. Basically, we have 3 unknown values, and therefore we need at least 3 equations to solve this problem. Now we apply the KLR and we select some loops, and the choice of the direction totally depends on you. At loop 1 we have equation G. At loop 2 we have equation H. At loop 3, which is the largest loop, we have equation I. As you can see, we only selected a few loops, despite that we can have more loops. The strategy here is typically done in a way that we reduce the number of devices necessary but must contain some or all the unknown. It is like choosing to have shorter equations, since each term in the equation corresponds to a device in the circuit, such as battery, resistors, bulbs, and others. A good strategy in drawing loops is to have a common intersection of the loops, like for this case they all intersect at the junction point C. We begin by simplifying the equations. Let us look at equation H, which will give us a simpler relationship of the currents 1, 2, and 3. We have equation J, which contains all the unknown. The other two equations contain only 2 of the unknown. We can substitute equation J to equation G and get equation K. Now we can equate equation K and I, since both have the same currents, and we get equation I. We now substitute equation L to equation I, and we have the current at resistor 3, which is -1 ampere. The negative value of the current 3 tells us that the assumed direction is incorrect and must be oriented towards the other side. We now substitute the obtained current I3 to equation I and we get I2. Similarly, we substitute the obtained current I2 and I3 to equation J and we get I1. We also do the same for equations E and F and we get the currents I4 and I5. Now we determine the equivalent resistance of the circuit. Here we apply Ohm's law, which is given here. But first we obtain the equivalent current is obtained using equation C, which gives us an equivalent current of 11 amperes. The equivalent voltage is just the voltage difference at points C and D, which is equal to the EMF, which is 13 volts. Now we substitute this to Ohm's law, we get the equivalent resistance of the circuit is about 1.2 ohms. Here we correct the direction of current at the third resistor positioned in the middle of the bridge circuit. Here we have a simulation of the problem using FET. We see that simulation also shows that the direction of the middle resistor goes in that direction. Simulations could help you to check if your solutions are correct or predict them. You can explore and examine the current of the resistors in FET Sims. Sample problem. The circuit shown in figure contains two batteries, each with an EMF and an internal resistance, and two resistors. Find the current in the circuit, the potential difference between points A and B, and the power output of each of the EMF batteries. Here we apply Kirchhoff's loop rule to determine the parameters using equation 11. We see that the current equivalent is 0.5 amperes. We determine the electric potential difference at points A and B. The potential difference can be calculated from point B to A and A to B. We calculate it first from point B and add the potential till we reach point A. We see that it is 9.5 volts. All the terms in the equation are positive since they represent an increase in electric potential. Now we calculate it from point A and deduct the potential till we reach point B. We see that it is 9.5 volts also. This is expected so that the sum of these paths would be 0 by loop rule conditions. All the IR terms in the equation are negative since they represent a decrease in electric potential. Now we determine the power output for each EMF source using equation 8. For the first EMF source we have 6 watts. For the second EMF source we have -2 watts. The negative EMF of 4 volts is due to the direction of the current, which runs from high potential or positive to the low potential negative. This type of problem is the concept behind charging batteries in cars. That is it for now, and I hope you learned something new today. For questions and comments you may send them to diyeslearningstuff@gmail.com. You may review the slide on YouTube at @diyeslearningstuff. Note, please do not forget to use your school email. Also write your complete name and class section. Thank you for listening and see you next module.